Well, without further ado, I think we'll get started, and while people are still slowly coming into the room. Hey, thanks to everybody for coming along to this month's EnviSMART. Really lucky to have Dennis Helsel joining us all the way from Colorado in the USA. My name is Brad Clark. For those people who don't know me, I'm from the University of Melbourne and the Australian Laboratory for Emerging Contaminants. I'm going to start off with an acknowledgement of country. We'd like to pay our respects to the First Nations people, wherever you may be joining us from for your meeting. For me in Melbourne, Wurundjeri people, pay respects to their elders past, present and emerging. The picture I got here, you may notice every month we put a different picture of the landscape. It's actually a beautiful Colorado we've got in the background. So just as that's where Dennis is actually joining us through his tea time, or 6 o'clock over there. EnviSMART is a free event, and which is only possible due to the help of our supporters. And I'd like to thank our principal partners, which are Agilent and Eurofins. And then we also have partnered with some other professional organisations, which is the Australian Contaminated Land Consultants Association, Water Research Australia, and CTAC Australasia and CTAC Asia Pacific. If you're not a member, become a member or get your company to become a member. And also, we also have support from Trajan and PM Separations. We've got an amazing program set up for you all this year. We've got I think a really fantastic program. And next month, we're actually going over to Europe to hear from Carolyn Mormont, and she's going to talk about ecotox and how you design those experiments properly so that they can be used by regulators. Then we're going back to the US actually by having Michelle Hadlick talking about neonicotinoids, insecticides, back to Australia with Jenny Storber talking about the environmental risks for deep sea mining tailings. And then Jen Lavers is going to present some of her great work on microplastics. Okay, without further ado, we're going to have a talk by Dennis for like 40 to 45 minutes. So get your questions all prepped and ready to go. And at the end of that time, we'll have you'll have time to ask him questions. What we'll do is get you to raise your hand through the chat function, and ideally you'll turn your camera and your microphone on and ask that question of Dennis. If you're too shy, you can also put your question into the chat and then I'll read out the question for you. Dennis we're very lucky because this might be one of Dennis's, might be his second last ever presentation. He's going to retire, he said, and he wants to move beyond his life and statistics. So Dennis has literally written the book on how you treat environmental data. And so we're really lucky to have him join us here today to share his knowledge of the things that he's learned from his career of working with environmental data. So thank you very much, Dennis. All yours.
Thank you, Brad. Well, this is a great opportunity for me as well. And I'll just switch over to the slide deck that dates me in terms of the terminology. But it's a great opportunity for me because I get to look back on what I have learned over the years and am able to pass a few things along to you, I hope. And so I've learned at least 2 things in 43 years of applying statistics to environmental science, and I want to pass those 2 along to you. Obviously, there are things that I think that kind of encapsulate 2 very important areas of statistics for environmental science. So the 2 things that we will be talking about this morning are to use methods that fit the objectives of your data. And those kind of platitudes are things I've heard over the years. So what I want to do is try to fill that out. What does that mean for you in a practical way when you are deciding what kinds of procedures to use? And I think for environmental science and people that are using field data in various types of media, water, air, soils, etc., biota, that it means that they will end up using distribution-free methods. So, and I will talk about what those are. And the second thing that I would like to pass along today is to use methods for censored data that were developed in other disciplines, particularly in medical statistics, for data that look something similar to nondetects, and we can take those and use them for data with nondetects. So for low-level contaminants, there are good methods out there that really are not being used yet. They're being used more frequently, but not as much as I would like. And so that's one of my goals with this talk, is to tell you about those methods and how you can learn about them. So we'll start with the first one, to use methods that fit the objectives of your data. This one goes along with a book that I and others wrote, and we wrote it back in 1992, I think it was published. And it has been revised, and so there's a new edition that came out in 2020. The title has not changed. It's Statistical Methods in Water Resources. It's available for free from the site. It's the U.S. Geological Survey's site, and I no longer work for them, but several of the other authors did, and the USGS was very willing to publish it. They published one version of the first edition. So the things I'm going to talk about tonight, this morning, excuse me, are in chapter 4, although they blend out into all the rest of the book. And I want to try to show you how that happens. So that's the reference. So let me start with a simple example. Which statistic would you use to meet your objective? I think you should think through that when you get started. And so what is a mean? A mean is one that's often chosen by people. And the mean is a per sample estimate of the total. So you're summing up data and then dividing by the number of observations, that's little n, and you get the mean. So are you really interested in a total? Does it make physical sense for you to sum up the observations that you're collecting to get a total? And the answer to that is often, not always, but often yes, when you're dealing with estimates of mass or volume or cumulative exposures over a period of time, things like that, where summing the data to get a total really does, it does give you some value. It's of interest in doing that. So here is a simple example with 10 tributaries. I should have added, by the way, an 11th number out here for the main stem of this stream, but I didn't, so we'll just kind of pretend I did. There are 10 tributaries here, and I've given you the loading, so the mass of some contaminant in some units, which I've completely made up the numbers, but one for each of these tributaries. And we'd like to know how much of the mass going into the reservoir at the right-hand side is contributed by those tributaries. So we would sum those up, those 10 numbers up. And we could represent that by dividing by 10, dividing by the number, and we get a mean of 1.72. And the thing I want you to notice is that 1.72 is higher than 9 of the 10 observations. So the mean is a measure of the center, but only in units of totals, only in units of mass. In other units, other scales, which we're going to talk about in a minute, the mean is nowhere near the center. So if being sensitive to 1 or 2 high observations, there's a 9.7 down here, which is quite a bit larger than any of the others. If having an observation down here that you're accounting for that's very high is a good thing, because this is a fairly high percentage of the total mass that's going into the reservoir. If that's a good thing that we've measured that, then you want to use a mean. However, change this slightly, same diagram, same numbers. Now I'm calling them concentrations. And we have 10 different streams, and I'd like to know, what's a typical value for these? What would be a number that if I went and sampled another tributary in this area, what's what's a concentration that I might expect it to be? That's a very different question. And so if you're interested in a typical value, the median is the middle of the observations on a scale of frequency, on a scale of occurrence. Half the values are below it, half the values are above it, and the median is 0.89, and that's quite a bit different than it was with the mean. So if you know that that's what you're interested in, a frequency, and I'll give you examples, frequency questions, then the median would be far more appropriate than the mean. And a key would be, ask yourself if you're sensitive to a few high outliers, and that's annoying to you, that you're tempted to throw away this 9.7 or do something else to minimize its effect, then you don't want a mean, because that's the most important value for a mean. If this is no more important than any of the others, then you want the median. And using a mean propagates out into a class of statistical procedures called parametric methods. And those are methods that deal with a mean. The median and other percentiles propagate out into another class of statistics called non-parametric methods. They're built on top of percentiles. And so this kind of question, one that you should ask yourself, is very relevant to which class of procedures I would use. So let me give you an example of that propagation. We'll go out to the situation where we have two groups and we'd like to know whether they are different. So the question is, are you interested in specifically in whether their means are different, whether the mass is different? If you are, and you were using a classical parametric procedure, you would use a t-test. And I'll spend a moment doing some statistical jargon, but not more than a moment, and tell you about a p-value, because I'm going to report it up here. It's 0.14 for the t-test with this data. P-value presents the strength of evidence in the data for there being no signal, no difference between groups in this case, or no trend, or no correlation. And so the smaller that p-value gets, the less likely it is that the no difference occurs. And so for this p-value, there's a 14% chance that you would see data like this when there really was no difference out in the real world. And that's not a strong set of evidence. And so the tradition, and it's only a tradition, but the tradition is to cut it off at 0.05, 5%. So this is not all that unlikely to occur when there is no difference according to the t-test. And so we would conclude that, well, I guess there's not enough evidence to say that these are different. Well, let's look at that figure. Do they look different to you? They look different to me. And in fact, all of the observations in the up gradient, this is groundwater concentrations of molybdenum, all of the concentrations in the up gradient well are higher than all of the concentrations in the down gradient well, or wells, I think it was, multiple wells for both of these groups. So this t-test is presenting to you one of the characteristics of parametric tests, and that is that they have low power. They have a low ability to see signals or differences that are actually there. When you use data of particular shapes, sometimes it's just one of the reasons that of that low power is just because of characteristics of a mean. But other are characteristics of the data themselves. And I'll tell you about those assumptions in a minute. But for right now, just remember that it has very low power. This is a test built on means. If you take the equivalent test built on percentiles and test whether the medians, it's actually a test for whether the entire set of percentiles, something called the CDF or cumulative distribution function, but it's just the set of percentiles. Are they the same in both groups? And you can see that the numbers are not too different than they were for the mean. And that turns out to be significantly different with a much smaller p-value. So this test has more power to say that they're different. And so what are you asking when you ask, are these different? a non-parametric test, a distribution-free test, this one is called the rank sum test, is testing whether, in a very simple way of putting it, whether some groups give you higher numbers than the other. And if that's what you want to know, you don't really care about a statistic called the mean. If you just want to know whether some groups give you higher numbers than the other, this is the test to do that, because this is the kind of question it is answering. It's actually answering the question, am I more likely, is there a higher probability? It's trying to say it in different ways, is there's a greater frequency of high numbers in one group than the other. It's a test on frequencies. So it depends on which question you're interested in as to which question you're interested in as to which test you would use. And the results can be quite different because there are restrictions with things like these parametric tests. They were built largely back in the 1930s and 1940s. The non-parametric tests are newer, and I'll tell you about another class in a minute, class of tests that are even newer. So these parametric tests test differences in means. One that has a test that has more than two groups is called analysis of variance, and many of you have probably used that. They answer questions, well, if you're talking about mass and volume and totals, and if you can assume that a normal distribution fits the data, and that groups have equal variability. So we can see back here that the groups do not have equal variability. There's a much higher variability in the up gradient group than the down gradient group. Field data of all of those media I represented earlier, this one happens to be water, field data usually have higher variability with higher concentrations. So they often, the things that I measure all the time, or did until I retired, had higher variability in some groups than others just because of the higher concentrations. Also, the data that I collected very, very rarely followed a normal distribution. A normal distribution did not fit it very well. Some people take the logs instead to try to assume that, try to get the data to look more like a normal distribution so you could use these tests. And that's really changing the wrong thing. You're changing the data rather than the test, because when you take logs, you're no longer testing for differences in means. So if that's really what you're interested in doing, you're not doing it then. You're testing differences in the mean of the logs, which is the geometric mean. And the geometric mean is one of the ways actually to estimate a median. So it has very little to do with the mean itself in the original units. Anyway, so you have all those restrictions. None of those restrictions really apply for non-parametric tests. They're testing for differences in the set of percentiles. They answer questions of frequency. Does one group have more frequent high values than the other? And they don't have the assumptions of data shape. They're distribution free. So most of the time, I ask questions of frequency, not because the tests are better, but because that's what I'm interested in. A trend test, unless you really specifically kind of twist it around, it really is a test in frequencies. Am I getting more frequent, higher concentrations later in time than I did earlier in time? And they are wonderful non-parametric trend tests that are actually the most popular tests for trend these days. So I get you to try to think about which kind of things you're interested in. Are you specifically interested in a mean, or are you just trying to test for how concentrations or other things you're measuring change, whether the numbers seem to increase or decrease going from one group to another? That's a frequency question. Or getting higher over time, that's a frequency question, etc. All right, then this third group of tests, which is even newer. These were envisioned in the 1930s. They're called permutation tests, and they test for any statistic, but we can use them for testing differences in means. And these permutation tests have one big advantage over the parametric tests, is that they don't have those same assumptions. So they don't require a normal distribution. They don't require equal variance. And they give you a test for means. So if you really are interested in means, statisticians in the last, I would say 25 years or so, have moved to using permutation tests rather than the older parametric tests. the tests were envisioned in the 1930s, but we didn't have the computing power to do them until the late 1980s or so. So they they solve the major problems that parametric tests have. And so if we run a permutation test on these two means, where the one mean up gradient is 16 times higher than the down gradient mean, all the data above are higher than all the data below, the permutation test on the means with the same data, without the assumptions that are actually dragging you down with the t-test because the data don't fit those assumptions, give you back a p-value of 0.002, 2 in 1,000, saying there's very little chance that you would see this kind of difference if there really was no difference in the means out in the field. So that difference between the 0.002 and the difference between the p of 0.14, which is a whole lot higher and so less powerful to see the difference, that's the consequences of using a test that requires things that are not realistic for the data that you're likely to find in air, water, soils, and biota. So if you're interested in truly in testing means, use a permutation test. It doesn't require all those other requirements that the older parametric tests use. So there's these three differences in tests, and I'm not going to go over the details, but they compute these p-values three different ways. It's how they use the data to get to the final result that differs among all three of them. And they use the data in different ways, and those different ways require, in one case, a lot of assumptions with the parametric tests, and many, many fewer or no really assumptions with the other two classes. If you want to know more about why they are that way, go look at the book that I referenced right at the beginning, Statistical Methods in Water Resources, and it is explained in some detail in there. What you should remember is that parametric tests have low power, low ability to see signals, low ability to see a correlation, to see a trend, to see a difference. And so when you use these kind of tests and your data don't fit these tests, and your data, I'll guarantee, will most of the time not fit these tests, like a t-test or a NOVA, then you will have low power and you'll miss contamination. You will miss things that are there out in the real world. So the alternatives are to use permutation tests if you're interested in means, or non-parametric tests if you're interested in frequency type, typical pattern questions. So here's my decision tree for how you do this. You'll notice there's no normal distribution kind of thing in this because that's really old school at this point. What's your objective? Mass, totals, chronic effects, long-term effects, test for means. Frequency, typical patterns, acute effects, test for differences in percentiles using non-parametric tests. Both of these classes are called distribution-free tests. And they're harder to really make a mess out of them. It's another reason to use them. If you're really not sure what you're doing with statistics, you won't make it anywhere near as many mistakes using these two classes of tests. Permutation tests, again, I'm probably running out of time, and they're fully covered in that book, but they can be expanded into more than two groups, so you can do them instead of analysis of variance. And they compute the p-values by taking your data and shuffling them around in thousands of different ways, and then get a p-value from that. What they're doing is they're generating a picture of what's called the null hypothesis, which is the no signal, there is no difference situation. And they're doing that by saying, if that no signal is true, then for the molybdenum data, there is no difference between these data, which means that this category from down gradient to up gradient has no meaning. So what I'm going to do is take all the data in both of the groups here, and I'm going to randomly assign them to these groups. So some of the up gradient groups will end up in the down gradient, some of the down gradient groups will end up in the up gradient. I'm going to shuffle them around, compute their two means, compute the difference between the means, and I'll hold on to that. And then I'll do that 10,000 or so times. And then I will look and see what's the one difference that we did here. We found a difference, looks like it's about 3.7. So that difference between the two means of 3.7, how does that rank in terms of all the ones we did when we shuffled? The ones when we shuffled were representing the no signal situation. So what did we get after that? This is the output from one of these permutation tests. Perm2 is a 2-group permutation test. So this is the permutation equivalent of a t-test. And this is the same data. Turns out there's 560 different ways to organize the data that are in this set of data. It's a fairly small data set, about 16 observations totally. So that's a pretty small number. So the software could just compute all 560 in a millisecond. So it computes all the 560 different arrangements of the data, assigning them to the two groups, and then says, my difference, which is about 3.7, how does that rank with all of these 560? Turns out, here's the p-value, 0.0018. So I rounded it to 0.002 before. Let's see, at 0.002, that's 2 out of 1,000, which is about 1 out of 500. So really, this is saying that the one that we got with the data is at the highest of all these 560. It's the most extreme. And that's why it's very unlikely to occur if there really is no signal out in the field. So that's how a permutation test works. And the key thing to remember, they have much more power when your data are not a normal distribution, when they have differences in variability. And they can be used to test for differences in means. And I'll skip over this just to say that when you have many more than 560, you have several 100,000 or 1 million different types of ways of reorganizing your data. The software usually does it about 10,000 times, and that's a good enough representation to give you an accurate p-value. You could make it 100,000 and get more precision on the p-value. It's not creating new data, it's just giving you this estimate of the p-value back and making that more and more precise with more repetitions, more different ways of rearranging the data. All right, so a summary for this first thing that I learned was to decide whether you want to test questions of mass volume or instead of frequency. And in my opinion, most questions in environmental science are of frequencies. If you are interested in mass volumes, means use a permutation, not a parametric test. If you're interested in frequency questions, use a non-parametric test. And don't rely on the older tests like t-tests and ANOVA. They have a considerable loss in power. So they produce false negatives, missing trends, or missing the effect of higher concentrations. And the reasons are that the data you put into it will be skewed. That means not symmetric, which means not normal, not a normal distribution, not a nice bell-shaped curve that's symmetric. Ours are not symmetric because we have a lower bound of 0. So we have a cutoff at the low end and nothing goes below there. And that right there produces skewness. We have unequal variance. Most of the time, the variability in a measurement is proportional to the concentrations of most of the parameters that are measured in laboratories. So use permutation tests. They work far better. So that's the first one. I believe you can ask questions in this chat window, and we'll hold the questions on that until the end. And I'll go through the second one here. So the second thing that I've learned over the years is to use the methods that came out of medical statistics for data with nondetects. And here's a book that I wrote. It is not free. This one is not free, sorry. It's called Statistics for Censored Environmental Data using Minitab and R. It's published by Wiley. I think they're only printing the ebooks at this time. I don't know why, if that's I'm sure it has to do with money. So, but here's a link where you can find it, or you can go on Wiley's website and stick in my name, Helsel, and put in censored. And between those two words, you'll get the book to come up. So this is the second edition, which was in 2012. And so what's wrong with just sticking in a half the detection limit or any other fraction of the detection limit? They all work very poorly. Why? The primary reason is it affects the variability of the data. Commonly, it will decrease it because you've just stuck in the same number over and over and over and over again. We often think about it as one number, and putting in something that's halfway between 0 and the detection limit or reporting limit. I'm going to use those terms interchangeably today because for these methods, it doesn't really matter. But for just putting in a half of that sounds like a good idea because it's halfway between what's possible. But it's not good because you're putting in the same number all the time. So it adds a pattern that was not there in the original data. And that is not a neutral thing. It produces poor estimates of things like confidence intervals. If the variation is too small, that means the standard deviation is too small. And if you're doing a confidence interval, then the confidence interval using a t-test is the mean plus or minus some number times the standard deviation. And if the standard deviation is too small, the width of the confidence interval is too small, and your endpoints are going to be too low on the upper end and too high on the lower end. And it has similar effects because the standard deviation is used in many, many different types of tests, including the t-test and the analysis of variance and in regression. So there are better methods than this that are available to us right now. They were developed starting in the 1950s, and you'll find them in software just in places that you didn't know what they meant. They're in places that are usually called survival analysis. And you can go to the book to figure out why. Okay, so if you just estimate the standard deviation and the low numbers are down here and the detection limit is right here around, the median is just slightly, the median is the middle line and it's just slightly, oops, sorry. The median is just slightly above 1. And so we have a detection limit of 2. That's what it is, a detection limit of 2. And so all the 2s become 1s because they're half the detection limit. Then this is a box plot, then the bottom value, the lowest thing you can get is a 1. And so everything below 2 is really kind of out of sync here. The data that were below 2, even the ones that are higher than 1 are called 1s, and all the data that are below 1 are called 1s. And so you've got this constant group of maybe a pretty high proportion of the data. And so where the original standard deviation was 1.02, and now it's 0.84, which is too low. And that's going to cause you troubles when you do tests. So people besides me have said this for quite a long time. Singh and others who worked as consultants for the US EPA at the time did a big simulation study and showed that when you put in a half the detection limit does not provide adequate coverage. That means the standard deviation is too low. And so this upper limit, the 95% confidence, upper confidence limit on the mean, is not high enough, even for percent non-detects as low as 10%. So sometimes in guidance, they tell you, oh, things are okay if it's 50% or less, or 20% or less, or 10% or less. And they found out that there were problems doing something as simple as a standard deviation and then using that to compute a confidence limit if you had as few as 10% non-detects. And so they concluded, don't do that. A paper that I co-authored way back in 1986 compared estimates for means, medians, and other standard deviations and found that substitution did not work as well as some of these other methods that have been used in survival analysis. And I'd be glad to send you a paper that tells you about that. So just to say, as an example for estimating the median, a better method, which is called regression on order statistics, or ROS, had 4.5 less bias than substituting a half the detection limit. So let's see. Here's an example of the invasive patterns, the problem with the patterns you put in when you substitute. Here's arsenic arsenic in leaves measured in ash weight in the lab, dry weight. So measuring it in dry weight, the leaves are ashed, heated gently, I guess. And then the arsenic in the ash weight in the ash times the percent of ash divided by 100 tells you the value you're going to be comparing from one sample to the other. And if the detection limit in the ash is 0.5, but the percent of ash, so what's not water, is going to differ between samples, so the resulting dry weights have many different detection limits. And there's things like this. Dilutions often do this when you've got things diluted in different proportions. Interferences. I've dealt a lot with inorganics and measuring trace elements when there's high salinity. Causes interferences that raises detection limits, and it would be raising it for some observations and not for others. And so the detection limits jump around. So when these detection limits jump around, and then the result of something that's not arsenic, not the thing you're trying to measure, then when you put in some fraction times the detection limit or reporting limit, some fraction, it's tied to this reporting limit, and it puts the pattern of that, in this case, water weight, or pattern of the process that caused the interference, or in soil, sometimes it's the amount of material in the bag that you send to the lab that determines the detection limit. And so it puts in a pattern. That's the amount of material that happened to be in that sample bag. So tying something to detection limit is not a good practice because it puts something into the data that's not there. Or a simpler example, maybe here's trends. Concentrations in a river over 20 years, the detection limits decrease over time. And so if the detection limits go down over time, it puts that pattern in there. Here's a collection of data over time. This was if we had no detection limits or reporting limits. If we did have reporting limits and they went down over time, this is the data, what the data look like when you do a trend test. And that decrease, just due to something that's a good thing, that the detection limits go down over time, puts a pattern in here that was not there in the river. And you could get a downtrend and report back how you had this downtrend in the river when it really didn't happen out in the field. So substitution times a detection limit is not a good practice. And there are better ways. And this is just another example with regression, so I'm going to skip it to save time. So other people, again, found that substitution and then running regressions where it's the Y variable that is censored doesn't work well. And this is a paper in Environmental Science and Technology, and I'll be glad to send you the reference if you want to go back and look at it. But it just tells you that substitution doesn't work well. So the thing is that there are better ways. So there's a software package, a system really, and called R, and a software package within that makes these things really easy. You don't have to really know the statistical procedures and a lot of what's behind them. It would be a lot like pull down menu kind of things in other software, statistics software packages, and they handle multiple detection limits, not just one. Oh, and here's the website, practicalstats.com training, and I put it here because next week, if everything goes right, on this website, I will have the course that I taught for the last 4 years or so on how you use all of these censored data methods. And that's how I made my living over the last 4 years, but as of April 1st, I've retired. So I'm putting it up there for free. So anyone could go there, and if you're willing to put the work in, it's somewhere between 1 semester and 2 semesters of material, I would say. So if you're willing to put the work in, people have done it in 3 months, doing it at night on top of their other job. But and some people have taken longer than that. But so if you're willing to do it, it's there. Here's just an example of what those kind of methods do. So here's a regression line. The dots are the detected observations. The dashed lines here represent the non-detects. They're just drawn from 0 up to the detection or reporting limit. So what's the value for those? The value is in the proportions, the frequencies of them, and how that changes with X. So when you look at these, you see that all of the non-detects are at the low end of weight. So these are total mercury in sediments, micrograms per gram, and no, actually in fish. I think that's in fish, and it's the weight of the fish. It's kind of a crude measure of size of the fish and age. And there's definitely a relationship. And the fact that the proportions here are higher, down below 400 grams of weight, and then they really don't occur above that, is additional information that these non-detects add in order to compute the regression equation. And we'll pull this line down appropriately at that low end. So that's just one example. Here is another example with neonicotinoids, just since Brad mentioned that. And this data comes from the Ontario Ministry of the Environment. And it's one of those pesticides, it's Thiamethoxam, and which is coated onto seeds before they're planted. And the question is, what's its effect on bees after those planted seeds, the plant, which is in this case corn, starts growing? And so they're comparing two groups. This would be a t-test kind of thing, just as it first emerges. Actually, maybe before, well, I don't know if it can be before. It was called post-planting, and then by the time the corn tassels appeared. So I think that is after the plants emerged. Must be. So here is the two sample t-test. And here's the two groups, the post-plant and the corn tassel. If you put in a half the detection limit and did the t-test, you get a p-value that's not quite significant enough, 0.058. It would certainly give me pause, but officially the difference was not found. Okay, and we really don't know below this detection limit much about the data other than it's below the detection limit. So, and all of data would have been put at 1/2. I think there was only one detection limit. And here is the same data with the censored method. This is in that NADA 2 package in R. And it's a two-group comparison. This is a non-parametric test, so I've switched there. It's called the Peto-Peto test, and it's asking the question, do I have more frequent high concentrations in one group than the other? And it has a p-value of 2 × 10⁻13th. So 13 zeros out before you hit that 2. That's a pretty different number than 0.058. And again, all the reasons we talked about before, parametric versus non-parametric, are here, and then also how they include the censored data information. And that's a pretty big part of this as well. So this kind of testing, including using t-tests, is used in developing no effect levels and adverse effect levels and other things. And so it really should be done in a way that accounts for the censored data. Okay, so what can you do now? Just about anything you want to do. It goes everything from plotting data, comparing its shape, to distributions. Is this a normal distribution or not? Confidence limits, hypothesis tests, regression models, trend analyses, high-dimensional plots, multivariate procedures, and really more than that. Can all be done in a censored data format. It's all been done by other people for a couple decades now. We just don't read the literature or use the methods from the medical statistics world. Here's a box plot of that Thiamethoxam data. There actually were 4 groups originally. I had compared the post-plant with the corn tassel, but you can do all 4 in an ANOVA type situation. But instead of ANOVA, use this command, which accounts for the censored data without substitution. None of these censored methods stick a number in for the non-detects. What they do is represent them as being less than 2, if they're less than 2. Somewhere between 0 and 2 would be the simple way. And how the proportions of those change, how the frequencies of those change. And so this comparison the 4 groups, the p-value is now down to 10⁻27th. So it's a very strong evidence that these are very different. And then it can do multiple comparison tests to see which which of these groups of time periods is different from the others. You can plot them in nice color plots and do all that kind of stuff. You can estimate what things look like. This assumes you say you think that this is a log normal distribution or some other distribution. You can create a model for what it might look like, or you can choose not to if you don't want to. This is a regression, and I will just say that you get back familiar things. There's a slope of 0.2436. Here's a p-value that tells you this x variable, which happens to be lead in kidneys of herons, is strongly related to lead in blood of herons, the same herons. And so that one could be used to predict the other. So you can get an intercept and a slope and get a regression equation out of this. You can get a p-value. All of this regression is done without substitution of numbers and does include the nondetects. You can plot the model. The regression line turns out to be a curve back in the original units. You can again see that the distribution of these nondetects, this is the small dashed lines here, are almost all at the low end of the kidney concentrations for lead. And as you get higher concentrations in the kidneys, you get higher concentrations in the blood and no more nondetects. There's one here, still below 4. So it uses that proportional information. Let's see. This is a trend test that gives you a trend line, and you can get p-values and find out there's a trend in one season, the dry season, and not in the wet season, and you can get the plots for those. So if you want more information, there was that textbook that I had before. There are videos that cover this kind of stuff. These have been free for the 4-year period. They're on the videos page of my website, which again is practicalstats.com. And the cost of complacency is why not substitute. The mystery of nondetects goes into more detail on how these methods work. How can they work when you don't stick a number in for them? And then the not a 2 video is for what you can do today, right now. It gives you examples in a little bit more detail than what I went through. And then the other ones go into more detail on some specific procedures like correlation and regression, how they work. So those are all there and you can view them for free. If you want even more information, starting next week, the course will be up. These are the 13 actually sections on this. It'll be under training, practicalstats.com. And you could go through that if you dare. Okay, I took a selfie here. In summary, after 43 years, these 2 principles will help guide your data analysis, I hope. So first, decide your objectives, particularly are you interested in mass volume? If not, you're probably asking frequency questions, and the non-parametric tests would be better. Or if you are interested in mass volume, cumulative exposure permutation tests would be the preferred method. And then second, use methods designed for censored data. And if you don't, and you substitute in numbers that can produce false positives, you could find trends that are not there, and it can produce false negatives. You could find differences that are, you could fail to find differences that are there. So that's the problem with the practical answer of why not substitute, because you're going to get at some fairly large proportion of the time the wrong answer. All right, thank you for attending. It's based on those 2 books that I listed before, and I'll just say questions, and we'll see if you have any questions. So Brad, how do you want to handle this?
Yeah, well, firstly, Dennis, thank you so much for a fantastic talk.